How we do in AP Stat? This is Chapter 9, Re-expressing Data. So to start this lesson, something that you may have been thinking about up to this point, if you've been following along in this series or if you're one of my students, is are there nonlinear regression models? The answer to that is yes. We only explore linear regression in AP Stat, though other types of regressions do exist, like quadratic, cubic, power, exponential, and we can even fit a sine or cosine curve for regression. However, though these might appear convenient, honestly, for reasons beyond the scope of the course, it is easier to just adjust the data to make it linear than to use more advanced forms of regression. It's easy to identify whether data form a line or not than to say, okay, do these data form a line or this curve or that curve or some other curve? Oh, these data look like they could resemble a parabola, but they could also resemble a sine curve. And we don't know which is best. We don't know which model is going to work best. And so we're just going to stick to lines, which means we need to do something to data. If we can't use regressions other than linear at this stage of the game, then we need to take our data and transform our data into a line and analyze it that way without corrupting the data. And that's what this section is all about. So here's the value of re-expressing data. So the graph to the left shows the relationship between fuel efficiency and the weight of a vehicle. And as you will quickly notice, though the relationship looks linear, the residuals suggest that a linear model is not best. After examining the residuals, the scatter plot looks kind of like a variation on y equals x squared. All right, it looks like a variation on that, maybe a little horizontal and vertical shifting going on, but it looks like a transformation of y equals x squared. That is a pattern, and we don't want any patterns in our residuals. So, since the original scatter plot kind of fits a curve of y equals 1 over x, like you know, to the right of the y-axis we have this sort of shape going on in the graph of y equals 1 over x, which you remember from algebra, pre-calc, those kind of courses. We can interpret the y-axis to be gallons per mile instead of miles per gallon. Now, why does that work? Well, if miles per gallon shows a relationship of 1 over x, if I were to find the reciprocal for my units, then my points would resemble the reciprocal of something like 1 over x, which would be some variation on y equals x, which y equals x, that's a line, all right? So then we get this linear fella right here. These points do appear to follow a linear pattern. And look at the residuals over here. The residuals look a lot better as well. So what are the goals of re-expressing data? Well, the first goal is to make a histogram more symmetric. A symmetric distribution is easier to analyze than a skewed one. So we see in this graph over here, it is very, 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 very right skew. All right, with some high outliers over here. We don't like outliers, we don't like skewness, because ideally in statistics, we like to use the mean and standard deviation to help us understand the center and spread of data. But that's only useful if we have a bell-shaped set of data in a histogram. So if I were to apply a logarithm to the assets on the x-axis, voila, I have this nice unimodal and symmetric distribution. Yeah, there's a little funny business over here, there's a little funny business over there, but logs are really good at taking big numbers and making them small, and taking really big numbers and making them almost as small, bunching the data into this nice shape. Now, a log is not a silver bullet. And yeah, we could run into issues applying logarithms. There are instances in which a log is not a powerful enough transformation, and we actually need to use something a bit more powerful. We'll get to that. But logarithms are very helpful in transforming data. So, goal number 2, make the spreads of several groups of data more similar. Now, this makes comparing between categories easier and can also remove outliers. So we see this set of box plots over here. Market sector is what we're talking about. So we have different areas of the market here, different categories within the market. And then we have assets in terms of hundreds of thousands. All right, so these box plots are kind of silly looking. It's just a big box. I mean, I can't really make sense of this. And also these outliers over here, they're not really fun. This is like everything's going on in this little section right here, and then there's that one outlier up there. Everything's going on in this little section, then we have a high outlier. And again, this box plot is legit just a box. It's very hard to interpret what's going on. So if I were to apply a logarithm to the assets, then all of the spreads look a bit more similar. Yeah, we still have a big box with medical, but it's at least the interquartile range looks a bit more similar to the others. It's not going to be perfect, but it'll make things more understandable. Again, logarithms can help us see patterns in data when otherwise it would be rather tricky. And you'll notice there are significantly fewer outliers. Finance does have 2 lower outliers, but 2 outliers as opposed to, my goodness, 6 over here, that's a major win. Goals 3 and 4. Goal 3 is to make the scatter plot, so we're talking about bivariate data, more linear. And goal 4, make the scatter plot spread out evenly rather than piling at one end. If you do transformation properly, if I were to speak properly, that'd be great too. If you were to do data transformation properly, you can kind of do 2 things at once, kill 2 birds with one stone. If we have a graph like this, all our data are bunched down here, and then we have some stragglers out here that are not in with the group. This is a horrible set of data to try to understand. But if we were to, again, apply a log to the assets, just like we applied a log to sales, it's not perfect, but the pattern is rather linear, and we get rid of this pile up over here on the left-hand side. So by using logarithms again, we take big values and make them small, and really big values and make them almost as small. Nice for making a linear pattern in our data. It's much easier to work with than this monstrosity over here. So we're going to identify some reasons to re-express data given a couple of data displays. In Chapter 8, we saw the ability of emperor penguins to slow their heart rates while diving. Here are 3 displays related to those diving heart rates. We got ourselves a scatter plot, a histogram, and a bunch of box plots. So what features of the data on emperor penguin dive heart rates from Chapter 8 might make us consider re-expressing the data? Take a moment, think about it, and unpause the video when you are done. All right, I'll assume we're ready to continue. I'm going to look at this histogram first, and I see that it is very right skewed. So we're going to make the histogram more symmetric. How we'll do it, that's a different story, and we'll talk about that in just a moment. Maybe a log will work, maybe something else will work. I don't know. But we want to make the histogram more symmetric. Make the spread of the data more uniform. Talking about these box plots down here, we have situations where it's just a box and an outlier, almost a box and 3 outliers, and then we have these over here, which are kind of all over the place. We would want to take these data and make them more uniform in terms of their spread. All right, and that might get rid of some outliers in the process. Again, how we do that, maybe a log would work, maybe we need something more powerful, I don't know. Finally, we want to make the scatter plot over here more linear. We see a curved 1 over x kind of shape in our scatter plot. That is not conducive to a linear model. Like we said in Chapter 8, up to about 4 minutes, This does look rather linear. It looks down and to the right, but as time of dive goes on, it does kind of do a 1 over x sort of thing. So a data transformation would be appropriate here to make the scatter plot more linear. So now for the part that you've all been waiting for. How do we properly re-express data without corrupting it? Our first strategy that we are going to look at is something our textbook calls the ladder of powers. The ladder of powers is helpful for determining how, or really if as well, data should be re-expressed. So how to re-express data and if we should express data differently at all. In these cases, the y variable is the one that is being transformed. So you have our response variable being transformed here, not the explanatory variable. Will we transform the explanatory variable? As long as the explanatory variable is quantitative, yes we will, but that's later, right? The further we go from leaving the data as is, which we will call 1, why do we call it 1? Just wait, you'll see. The more powerful the effect. Going too far, however, might actually make our data bend the other way. So if we have a nonlinear model and we alter the data a bit too much, the nonlinear model might just go the other way. And we don't want that either. That's not helpful. So we want to do this just right. So let's run down the ways in which we can re-express data. And the method that our textbook opens up with is the ladder of powers. This is not the only template for how to re-express data, but it's a great place to start. So the ladder of powers is helpful for determining how data should be re-expressed. In all these cases, the y variable is the one that is transformed. Sometimes we will transform the x variable as well, the explanatory variable, but for now we're going to stick with the y response variable. So the further we go from leaving the data as is, which we call 1, and I'll show you why that's true in a second, the more powerful the effect. But if we go too far, say our data are curved one way, like we have a scatter plot that is curved up, if we were to make too powerful of a transformation, we would just curve the data the other way, and that's not good. All right, so we only want to go as far as we need to go. So the mildest of transformations, if we transform the data at all, is to simply square the data values. In other words, if I have a y value of 4, that would become a y value of 16, all right? And the x value would just stay the same. One is leave the data as they are, all right? So by now you may be seeing a pattern. This 2 refers to squaring the data, and 1 is just set it to the power of 1, which is not doing anything at all. 1/2 is apply a square root to the data values. Exponent of 1/2 is the same as a square root. In other words, a y value of 4 becomes a y value of 2. Square root of 4 is 2. 0. Now, we use the number 0 loosely, but 0 refers to logarithm. Sometimes I will spell logarithm with a 0 instead of an O when we're doing examples in class, just to refer to it as 0 like our textbook does. But applying a logarithm is more powerful than applying a square root, and I'll show you why that's true in just a moment. So a y value of 4 would become a y value of log of 4, which is an irrational number. And frankly, I don't know it off the top of my head. Negative 1/2. We are going to apply a negative reciprocal square root to data values. All right? In other words, 4 would become negative 1 over the square root of 4, which is 2. All right? Now notice the order of operations here. I would first find the square root of my data value. So the square root of 4 is 2. Then I would find the reciprocal of that square root. So that's 1 over 2. And then I make it negative. And we'll talk about why we make it negative in just a moment. So negative 1 over the square root of 4 would be my transformation if my initial y value were 4. And the most powerful transformation we have is use the negative reciprocal of the data values, which we refer to as -1. So in other words, a y value becomes, it's opposite reciprocal. 4 would become -1/4. Okay? So why the negative? You notice the asterisk right here and the asterisk right here. The negative preserves the direction of the relationships. You may remember earlier in this lesson, there was a set of bivariate data that was curved down and to the right. Once I applied a transformation to that data, the data appeared more linear, but it was going the opposite way. It was up and to the right. All right? If we want to preserve the direction of our data, then we can make for the reciprocal square root and the reciprocal, we can make it a negative reciprocal square root and a negative reciprocal to keep the data going in the same direction, just more linear. Okay? So this may be helpful for some of you. This may not be helpful for some of you. That's okay. But I want to show you this graph right here. I've paired each of these transformations with its respective curve. So for example, for this here, this curve pairs with squaring. This is y equals x squared. This is y equals x. This refers to leaving data as they are. And 1/2 is apply a square root to the data values. That's here. Logarithm is the reason that we use 0 for logarithm, at least I think, when people refer to ladder of powers, they use 0 for logarithm. It just looks like a more powerful square root. It's a square root that pulls things closer to the x-axis. It's basically a more powerful square root. That's at least how it behaves here. And then you have the negative reciprocal square root in the black and the negative reciprocal over here. And the more that the curve tends toward or away from the x-axis relative to y equals x, the greater potency of the transformation. So if this is our don't touch anything non-transformation, if the data fit a line, we don't change anything at all. If the data are curved, then we need to perform some kind of a transformation to it. And a transformation that involves going further from the x-axis or toward the x-axis or really toward the x-axis or really, really toward the x-axis or really, really, really toward the x-axis, those are transformations that can make our data straighten out. So the first step of the ladder of powers we're going to consider, the mildest of adjustments to our data, would be to square the y values, which we would refer to as 2. So it's generally the most mild of adjustments. And squaring the data values, specifically the y values, helps most when the data are skewed to the left. So we see a left skew model over here. If I were to square all the data values, it's not necessarily a bell, but it is certainly rather symmetric. And symmetric data are easier to work with than asymmetrical data. Our next option is to just let data be as they are. When data are already almost linear or can assume both positive and negative values or don't have boundaries, minimum or maximum possible values, the data don't usually benefit from re-expression. It's best to just make like the Beatles and let it be. Our next option is to apply a square root. Applying a square root is often helpful to re-express data that involve some kind of count, all right? So the frequencies here involve counts, all right? It's the number of siblings, okay? And what often happens with counts is things tend to be a bit right skew. You have a couple of high data values over here, but things are really bunched to the left. What we want to do is bring these fellas back into the fold. Re-expression yields a curve like this. It's not perfect, but it's certainly more symmetrical than what we started with. So when we're dealing with some kind of count, it's nice to have a square root at hand. Now we're going to look at 0. Apply a log, just as I warned you, I spell it with a 0 instead of an O sometimes. Applying a log to the data values that can't be 0 or negative can be helpful, all right? Let's talk a little algebra here, the domain of the logarithm, all right? A logarithm, without any transformations, a logarithm has a domain of positive real numbers. That means that we cannot input 0 into a logarithm, all right? So if 0 is not a possible data value, a log is a good choice. And a log is usually helpful for skewed data left or right. What's awesome about a logarithm is it can take big numbers and make them small. It can also take really, really big numbers and make them almost as small. So it's great for condensing data that's spread over a wide interval. So say we have these data right here. Most are bunched over here to the left, but we have, it really trickles down over here, but apparently there's something going on out here that's so small that we can barely see it. But we don't like outliers in data analysis. If we can make them not outliers through a transformation, that's awesome. So if we were to take a log, we would get something that is beautifully symmetrical and easy to analyze. Now, one question that may immediately come to mind, Mr. DeClerico, why are these values over here negative? Well, if you know a bit about logarithms, if the original y value is between 0 and 1, a logarithm is going to output a negative number, okay? So if you remember back to algebra, if you graphed a logarithm function with no transformations, no shifts or anything like that, the x-intercept is at x equals 1, and everything between x equals 0 and x equals 1, the function is negative, all right? It's below the x-axis. So we should not be surprised to see negative outputs when applying a log to all the y values because there is an interval of inputs for which the log outputs a negative number. Now we are going to look at the negative reciprocal of the square root and the negative reciprocal. These are the most potent adjustments, okay? So we have opposite reciprocal square root, or just the straight up opposite reciprocal. They are sometimes helpful for units that are ratios. For example, miles per gallon. That's similar to something we saw earlier in this section. We were able to switch miles per gallon into gallons per mile and straighten out the data. Dollars per hour, bananas per strawberry. If you get this reference, you are blessed. All right, etc. If we have a ratio, then sometimes these are helpful. And remember, it's the negative reciprocal or negative reciprocal square root, not just the reciprocal, preserves the direction of the association. Okay, so we want to apply, in this case right here, not just a reciprocal 1 over y, but a negative reciprocal. If I were not to make this negative, this data, which look a lot better than what I see over here, would start going up, and that's not the direction that we want our data to look like. So now that we know all the data transformations that we can employ in AP Stat, let's look at a couple of problems that would involve you making a judgment call as to where you would start on the ladder of powers when trying to transform the data. It's not necessarily what's going to work best, but where would be a good place to start considering the type of data you're working with. So consider 1, 2, and 3. Note that number 2 starts down here and continues up here. Look at numbers 1, 2, and 3. See if you can figure out the best place to start, and there are correct answers to each, although 3 is a little tricky. There are correct answers to each, yeah, give it a go, see what you think is going to work best, and unpause the video when you are done. Okay, I'll assume we're ready to continue. Let's look at number 1. So you want to model the relationship between the number of birds counted at a nesting site and the temperature in degrees Celsius. Scatter plot of counts versus temperature shows an upwardly curving pattern with more birds spotted at higher temperatures. What transformation of the bird counts might you start with if you're looking to transform your data? Well, there's only one word that you need to know. Birds counted. All right? So when we're dealing with counts, applying a square root is a good idea. So we'd use the 1/2 transformation, apply square roots to the counts. All right? So you want to model the relationship between prices for various items in Paris and Hong Kong. The scatter plot of Hong Kong prices versus Parisian prices shows a generally straight pattern with a small amount of scatter. What transformation, if any, for the Hong Kong prices might you start with? So there's no reason to transform this data, all right? Make like the Beatles and let it be. So you want to model the population growth of the U.S. over the past 200 years. The scatter plot shows a strongwardly upwardly curved pattern. What transformation, if any, of the population might you start with? Well, we are definitely transforming this data. And population is a count, all right? But it's a big count, all right? So there's a couple of things we could do here. So this one may take several attempts. Let's just get that out of the way. Start at 1/2, we could apply square roots to the population since the data are counts, but since these are really, really, really big counts, we want something that's going to take really, really big numbers and make them small, all right? So we'll probably need something stronger. So if 1/2 doesn't work, we would proceed to 0, we apply a logarithm to the counts, and that'll work out just fine.